So the title, as Katya said, is simultaneous determination of internal source and coefficient of a diffusion equation from a single boundary measurement. So we'll try during this talk to see what is a different notion that appears in this title. So what I would like to say is that this talk is partially based on some joint work with Ziu and Lee, Yik and Liu, and Masairo Yamamoto. So let me start with the general statement of our problem. For this purpose, let us consider the following equations that we considered for the time variable lying in the interval of time 0, capital T, and the space variable lying on capital M, which will be a compact Riemannian manifold with boundary of dimension d bigger than 2. After that, in this time-space domain, we consider the following equations with a time derivative to the power alpha, where alpha will be lying on the interval 0, 2. I will specify a little later on what I mean here by the time derivative to the power alpha, when alpha is not integer. And the following equations that we consider with the Laplace-Beltrami operators and several coefficients. To this equation, we associate also a source term containing a time-dependent function and a function depending only on the space variable. After that, we associate to these equations the following initial boundary value problem by fixing a directly input capital phi on the boundary of the manifold and some initial condition which will be associated to the power of derivation alpha. In particular, for alpha between 1 and 2, we fix the initial derivative at 0. So let me specify here what I mean by this time derivative to the power alpha. So when alpha is equal to 1 by this time derivative, I mean the usual time derivative, and our equation will be a parabolic type of equations, classical diffusion equation. However, in the case alpha not equal to 1, by the time derivative to the power alpha, I mean here the fractional derivative in the Caputo sense of order alpha given by the following expressions. So I will skip for the moment the reason why we make this choice for the time derivative to the power alpha, so the non-integral power of derivation, but I will come back to this notion and I will specify why we make this choice later on in this talk. But for the moment, let us skip that part. And let us consider the statement of our inverse problem. For the statement of our inverse problem, we need to fix nu to be the outward unit normal vector with respect to the boundary of our manifold and the associated normal derivative. After that, we will consider on the boundary of our manifold two open sets, gamma in and gamma out. And the main idea here will be to apply an excitation on the part of the boundary gamma in, which will be associated to our direct input. It will be the support of our direct input, and to associate to this unique excitation of the system some measurement that we want to make on the part of the boundary gamma out. So the idea will be here to apply excitation and measurement on the boundary of our manifold, which will be the accessible part of the system. And the goal will be to determine what happens inside the manifold, which is the inaccessible part of the system. And what we want to determine will be one of the two internal sources appearing in our equations, that is the source term or the initial condition, combined with several parameters of the equations corresponding to the Riemannian manifold up to isometry, the different coefficients appearing in the equations, and the order of derivation. So the kind of measurement that we want to consider will be taken on a full interval 0, capital T0, from some suitable values of capital 0, but they will also take the form of capital T0 minus delta, capital T0, with delta as small as we want. So I will specify that a little later on. And as I said, the excitation of the system will be given by the direct input, which will be supported on the part of the boundary gamma. So now let me say a few words about the motivations of our problem. Let me start by the description of our equation in the case alpha equal to 1. So for alpha equal to 1, we consider a convection diffusion type of equations, which are used in order to describe the transfer of mass or heat through two processes, that is the convection and the diffusion, and this for different physical quantities such as particles, energies, and others. In the case alpha not equal to 1, our equations are called fractional diffusion equations, and they are associated to anomalous diffusion phenomena. What we can say about the derivation of this type of equations is that the derivation comes from model based on continuous in time random walk. And for the derivation of this type of equations, we can, without being exhaustive, we can mention the work of Scher, Lax, Bouchot, Georges, but also Metzler and Klafter. Beside the derivation of this type of equation from probabilistic model, what we can also say is that these equations are associated to subdiffusive model, in the case alpha between 0 and 1, and to superdiffusive model when alpha is between 1 and 2. And we talk also sometimes about fractional wave equation in that case. And what we can also say is that this equation have been successfully used for describing several models appearing in diffusion in porous media, diffusion in complex fluid, as well as several models in finance and biology. Whether we consider the case alpha equal to 1 or alpha not equal to 1, the non-integral values of alpha, in both cases, the goal of our inverse problem will be to determine the source of diffusion, which will be given by one of the internal sources, whether it is the initial condition or the space-dependent part of the source term, simultaneously to some information about the diffusion process, which can, for instance, be given by the convection term B, which is associated to the velocity field of the moving quantity, as well as some other parameter, which will be associated to the density of the medium. So this will be the goal of our inverse problem. So now let me go back to this notion of time fractional derivative in the Caputo sense, and let me explain why we make this choice before we move back to our results and the description of what has been done so far for our problem, as well as our own results. So let me specify why we make this choice of the time fractional derivative in the Caputo sense. In order to understand this point, you need to go back to the usual derivative, to which you can associate the following integral operator, and you can see the usual derivative as the invert of this integral operator modulo constant function. And this is the idea that we'll follow in order to define non-integral power of derivation as we have introduced in our equations. To do so, we need first to define the non-integral power of composition of this integral operator. And to do that, let us start by considering the usual composition of this integral operator, capital E. And what we get by making the composition of this operator is the following expressions. Applying a simple Fubini theorem, what we will be leading to is the following expression involving a convolution term. And from this convolution term, we can easily get non-integral power of composition of this integral operator by the following expression. So with this expression, which of course coincide with integral, whose values coincide for integral values of alpha with the usual composition of the integral operator, we get actually a definition of non-integral power of integrations. And the idea now will be to define non-integral power of derivation as the inverse of this operator modulo polynomial function. This idea will lead us to two definitions of fractional derivative or non-integral power of derivation. The first one will be the inverse of the left-hand side of the power alpha of the operator capital E. So the left-hand side inverse will be given by this fractional derivative in the Riemann-Liouville sense, which is expressed here by these expressions, whose idea is to first integrate to the power integral part of alpha plus 1 minus alpha, and then to apply derivative of order integral part of alpha plus 1. So if you take the difference between what we have derived and what we have integrated, you get exactly alpha. The second definition that we get is a fractional derivative in the Caputo sense. So this time we consider the inverse on the right-hand side of the integral operator to the power alpha. And this fractional derivative in the Caputo sense will correspond this time to apply the derivation. So you start by the derivation and then integrate. So what we can say is that we have two definitions. And at some point, we need to make our choice and to specify which definition we will consider. For this purpose, let me first start by explaining what these two definitions have in common. And what they have in common is their values for function vanishing up to some suitable order at 0. Indeed, if you pick some sufficiently smooth function vanishing up to some sufficiently suitable order at 0, you can see that these two definitions coincide. The definition of fractional derivative in the Caputo sense coincide with the one in the Riemann-Liouville sense. You can even go further and see that actually these two definitions will coincide with the definition of non-integral power of derivation given by Laurent Schwartz in his classical textbook, Théorie des distributions, a definition which can be extended to distributions supported on 0 plus infinity. To see this, you need to first extend your function f by 0. And what you can get from that is that these two definitions of fractional derivative will coincide with this expression of fractional derivative given by Laurent Schwartz in terms of convolution of two distributions supported on 0 plus infinity. So here you have actually the finite part of this function, which corresponds to a distribution supported on 0 plus infinity. So this is what these two definitions have in common. Now, let us move to what will make the difference between these two definitions. The first thing that can make the difference is the behavior of this fractional derivative or non-integral power of derivation applied to constant function. While the definition in the Caputo sense will vanish constant function, the one in the Riemann-Liouville sense will not vanish them. The other difference is arising in the statement of Cauchy problem with these two definitions of fractional derivative. While fractional derivative in the Riemann-Liouville sense will lead us to initial condition corresponding to some non-local expression, Cauchy problem stated for fractional derivative in the Caputo sense will lead us to the usual initial condition. And this will allow us to make the difference between these two definitions. And what we can say is that the definition of fractional derivative in the Caputo sense will be more suitable for the model that we want to consider. And this is the main reason why in all this talk, the derivation to the power alpha when alpha is not an integer will be the fractional derivative in the Caputo sense. So now let me go back to our problem and let me recall what is known so far about our problem. And I will start with the recovery of coefficient, only coefficient, in the case alpha equals to 1. So the first class of result that I will mention is results stated from infinitely many measurements. So as I said, the result that we want to consider is a result stated with a single measurement. Measurement associated to one excitation. Result based on infinitely many measurements correspond to result with excitation, with measurement associated to excitation which are lying in a space of infinite dimension. So for instance, you can consider a problem with data which are stated from the Dirichlet to Neumann map. So here the result that I will mention are stated with something close to parabolic Dirichlet to Neumann map. So in this class of results, the first result that I would like to mention is a work due to Caputo and Kian, where these authors have proved the recovery of several classes of coefficients by means of this type of infinitely many data. The other result is a result due to Kachalov, Kurilev, Lassas-Mondash, where the authors extended this approach of Caputo and Kian to the recovery of a Riemannian manifold up to isometry. So this is what we can say for results stated with infinitely many measurements. Now let us move to results stated with a single measurement. In this class of results, the first type of result that we can mention is result based on the so-called Böckler-Kilbanov approach, which is mainly based on suitable application of Kahneman estimate. In this category of result, we can mention the work of Yamamoto-Zhu, but also of Yuan Yamamoto, who have proved the recovery of some class of coefficient by means of this approach. So the first thing that we can say for the application of the Böckler-Kilbanov approach for parabolic equations is that it does not only require boundary measurements. Boundary measurements are not enough for proving recovery of coefficient with this approach. You need also to know your solution at one fixed time inside the domain. So this means that you need information on the inaccessible part of the system for your solution in order to be able to recover coefficient with this approach. As an alternative approach, Avdonin and Seidman have introduced in 1995 an approach which is mainly based on the construction or consideration of suitable Dirichlet input that allows from a single boundary measurement of parabolic equations to recover the full DN map of the associated elliptic problem. So combining this with the result of Sylvester and Ullmann, Avdonin and Seidman have been able to recover a zero-order coefficient. This approach of Avdonin and Seidman has been extended in the 2D case by Cheng and Yamamoto to the recovery of the convection term. So if you make the comparison between this approach and the one of Böckler-Kilbanov, you can see that the approach of Avdonin and Seidman require only measurement on the accessible part. So you make excitation on the boundary and you make measurement on the boundary. You don't need knowledge of the solution inside the system at one fixed time. So in that sense, the approach of adenine and Seidman would be more suitable. However, the bad point of this approach of adenine and Seidman is that it is based mainly on some analyticity property, which will not be suitable for stability. So here we can see the other difference, the other bad point of this approach, since the approach of Bergen-Klibanov would be quite suitable for stability results. So this is what we can say about this problem in the case alpha equal to 1. Now let me move to results stated for alpha not equal to 1, and still results devoted to recovery of coefficients. So the first thing that we can say is that this class of inverse problem, that is recovery of coefficient for time fractional diffusion equation, has received less treatment than the one for parabolic equations. Among the different results that we can mention, we can first refer to the work of Lee, Emanuelov, Yamamoto, who have proved recovery of some class of coefficient by means of infinitely many measurements made on measurement given on the full interval in time 0 capital T and the full boundary of an open set. So here the results are stated on an open set and not on a Riemannian manifold. The other class of result that we can mention is results that we have obtained with Oksanen, Sokorsi, Yamamoto, where we have obtained results comparable to the result that will be introduced, with the exception that we have not treated the recovery of internal source, just coefficient and Riemannian manifold. However, in this result, we consider infinitely many measurements, but these infinitely many measurements are made at one fixed time. The other class of result that we can mention is some work that we have obtained with Sokorsi Yamamoto, where we have considered the specific case where the power of derivation depends on the space variable. This is some phenomenon that appears due to the presence of heterogeneous region, making variation of this power alpha. And what we have been able to do in this work is to recover actually this power alpha, power of derivation. So all the three first results that I have mentioned are all stated with infinitely many measurements. Concerning results stated with single measurement, beside the one that I will present later on, I can only mention two works. The first one is the one that we have obtained with Yamamoto, where we have proved recovery of zero-order coefficient in the specific case of cylindrical domain. So our approach works only for cylindrical domain. However, we have been able to get stability result in that work. And the other one is a result due to Elin, Lassas, Guilhem, Zhang, where these authors have been able to prove the recovery of a Riemannian manifold up to isometry by means of a single boundary measurement corresponding to some internal measurement. So here the data considered by these authors correspond to a single application of the source to solution map. So the first thing that we can say is that beside the work that I will present a little later on, there is no results for time fractional diffusion equations and the recovery of coefficient for time fractional diffusion equations stated with a single boundary measurement. We have only two classes of results with single measurements for general domain. I mean here, single boundary measurement for general domain or general manifold. So the only class of results that we know from single measurement is the one that we have obtained with Yamamoto using boundary measurement for cylindrical domain, and the one here using internal measurements. So the last category of results that I would like to recall correspond to results dealing with simultaneous recovery of source and coefficients. So the first thing that we can say is that the recovery of source has received a lot of treatment, whether you consider the case alpha equal to 1 or alpha not equal to 1. Many authors consider the recovery of a source term appearing in this type of equations. However, as far as I know, at least, there is no result, even for the alpha equal to 1, dealing with the simultaneous recovery of source and coefficient. And here, I mean source and coefficient depending on the space variable. Even if you take a look at this problem for all PDEs, what you can see is that there is only some restrictive results devoted to the simultaneous recovery of source and coefficient. Among this class of results, we can mention the work of Liu and Ullmann, who have treated this so-called thermoacoustic and photoacoustic tomography problem, where they have tried to recover from a single measurement of a hyperbolic equation, single boundary measurement of a hyperbolic equation, the sun speed coefficient and the initial value of the solution. So here, the authors have not considered Dirichlet excitation, But even with a direct excitation, it is not clear how you can solve this type of problem from a single boundary measurement of a hyperbolic equation. A general coefficient, of course. Okay, so this is what we can say about what is known so far. Now, let me state our own results. So in order to state this result, I will start by the definition of our Dirichlet input. Indeed, here we will consider quite general Dirichlet input, and all our results will be stated with the same class of Dirichlet inputs. In total, I will present 5 results, and all these 5 results will be stated with this type of Dirichlet input. So in the definition of this Dirichlet input, we need to first fix τ1 and τ2 in our interval in time 0, capital T, in such a way that τ1 is strictly less than τ2. After that, we introduce an increasing sequence, tk, starting at τ1, and whose limit will be τ2. We fix also pk to be some arbitrary value that we fix on the interval 0 plus infinity. And we define the function pk that will give us the behavior in time of our Dirichlet input. So this function pk are some smooth function which are equal to 0 on the interval 0 t to the index 2k minus 2, and they are equal to pk on the interval t to the index 2k minus 1 to plus infinity. So actually what is important in the construction of this function pk, which will give us the time behavior of our Dirichlet input, is what happened between c to the index k plus 1 and tk on the interval t to the index 2k minus 1 and t to the index 2k. Indeed, in this interval in time, p to the index k plus 1 remain at 0, while pk take its final value. And this is actually the main point in the construction of this function. So this kind of function will give us the time behavior of our Dirichlet input. We need now to complete the construction of our Dirichlet input, which will take the following form. First of all, we introduce a sequence bk, which will allow us to have this sequence to be convergent. Then we introduce the function key, which will localize our Dirichlet input on the part gamma in. So this cutoff function will be equal to 1 on gamma in prime, which in practice can be as close as we want to gamma in. So since we consider only single boundary measurement, we may assume somehow that gamma in prime is gamma in. After that, we complete our construction by introducing the sequence of function eta k lying in H3/2 of the boundary of our manifold, and chosen in such a way that the span of the function eta k will be dense in H3/2, and the norm of this function is equal to 1. And after that, we introduce our Dirichlet input corresponding to the infinite sum of these expressions. And due to our different choice, what we can say about this Dirichlet input is that it is C2 in time as a function taking value in H3/2 of the boundary of our manifold. So using this Dirichlet input, we are now in position to state our main results. For our first results, we will consider the Riemannian manifold to be the closure of an open set which is C11, and an open set of RD D bigger than 2, of course. And we consider the following initial boundary value problem with an equations containing a weight function, a conductivity, and a zero-order coefficient. We have also a source term, still of the form time-dependent function times space-dependent function, and some initial condition. So here, the main assumption that we will make is that the time-dependent part of our source term is not uniformly vanishing, and its support is contained in 0 τ1 with respect to the time variable. So this 0 τ1 is given here. It's the starting point of this function tk, from which we define the function pk. So this is the main assumption that we made. And now we can state our first result. So we would like to recover simultaneously one of the two internal sources, that is the source term or the initial condition, and two among the set of three coefficients appearing in our equation from a single boundary measurement corresponding to the measurement of the flux, which correspond to the normal derivative of our solution weighted by the conductivity that we consider on the interval in time 0, capital T0 with respect to the time variable, and on the part of the boundary gamma out. So here, capital T0 is arbitrarily chosen between τ2 and capital T. τ2 being the limit of this function tk. So this is the result that we want to prove. And let me first state that actually the recovery of two coefficients among the set of three coefficients will be an optimal result due to some obstruction. We cannot get better result than the recovery of two coefficients among the set of three coefficients. Now, let me state our first result. So in this first result, we consider first some geometrical restriction imposed on the part gamma in prime and gamma out. So I recall here that gamma in prime is the part where this cutoff function is equal to 1. And this condition somehow can be seen as the idea that you fix one of them arbitrary, gamma out or gamma in prime, and that the other is a little more than the complementary with respect to the boundary of our open sets. So this is the kind of geometrical assumption that we apply to the part where the excitation are made and the measurement are made. After that, we consider two sets of coefficients and two sets of internal source. So here we assume that one of these sets of coefficient is known. This is the assumption that appears here. And one of the internal source will be also known. This is the assumption that appears here. To that, we add some knowledge of the coefficient at the boundary. And with this type of assumption, what we prove is that if the normal derivative of the solution of our problem with the direct input that we have defined and weighted by the conductivity coincide on the part of the lateral boundary corresponding to the interval in time 0 capital T0 and with respect to the space variable restricted to gamma out, then the two unknown coefficients coincide and the unknown internal source coincide also. So we can get simultaneous recovery of all these parameters in one shot. This is our first result. For our second result, let me consider a little different situation. So this time, we pick this power of derivation to be lying in 0, 2, but not equal to 1. So we exclude this time the parabolic case. And we consider the same problem, but we would like to restrict our measurement to any interval in time of the form capital T0 minus delta, capital T0, where delta can be as small as we want. This is the main point that we change from theorem 1 to the next theorem that I will introduce here. So as I said, we pick here alpha to be not equal to 1. So we are in a purely fractional diffusion case. We add some regularity to the different parameters and also some knowledge of the coefficient on the part where we made our measurement, the part gamma out, to which we add also some regularity assumption that I will not specify here. And after that, we can state our result as follows. If we know the normal derivative of our solutions and the normal derivative of this elliptic operator applied to our solutions on any interval in time of the form capital T0 minus delta capital T0 with delta that can be as small as we want, and on the part of the boundary gamma out with the same assumption in terms of restriction on gamma in prime and gamma out, then we can get exactly the same result as in theorem 1. So this is the first extension of our result stated in theorem 1. Now, let me state the last result that we would like to consider on an open set. Then we will move to results stated on a Riemannian manifold with boundary. So here, we consider this time our equation with a convection term. That is a first order coefficient, which in our context can be associated to the velocity field of the moving quantities. And our excitation will not be restricted on some part of the boundary, since here the cutoff will be equal to 1. So we consider excitation in all the boundary of our domain, and we will make also measurement in all the boundary. And the idea this time will be to recover the power of derivation, which is a constant, the weighted function, the convection term, and one of the two internal sources by means of a single boundary measurement comparable to the results stated in theorem 1, with measurement made in all the boundary of our domain. And the result that we obtain is exactly what I've stated before, in the sense that if we know the normal derivative of our solution in the boundary of our domain, then we can recover simultaneously these sets of parameters with the power of derivation, which is not the same this time, and one of the two internal sources. So now let me move to our results stated on a general smooth Riemannian manifold with boundary. So here we consider the following problem with the Laplace-Beltrami operator, which appears here, and a zero-order coefficient. And our goal here will be to determine with two different types of measurements, measurement on the full interval in time 0 capital T0, but also measurement on any interval in time of the form capital T0 minus delta capital T0, where delta can be as small as we want. So we want to determine from this type of measurement the Riemannian manifold up to isometry, the zero order coefficient simultaneously to one of the two internal sources. This is our second class of results stated for Riemannian manifold. So here, the first result that we obtain can be stated as follows. So we consider two Riemannian manifolds that have the same boundary and for which the metric coincide at the boundary. After that, we consider two classes of internal source and coefficient. And we make this time our measurement for gamma in equal to gamma out arbitrarily chosen. So the part where we made our measurement will coincide with the part where we apply our excitation, and it is arbitrarily chosen. And here, in addition, our assumption will be that one of the internal sources will be fixed at 0. So since we deal with different kind of manifold, we cannot say that they coincide. We need to fix them at 0. And we consider u in index j to be the solution of our problem for the parameter of index j. And what we can show is that the knowledge of the normal derivative of our solution on the interval in time 0 capital T0 and on the part of the boundary gamma out allows us first to state that the two Riemannian manifolds are isometric. And secondly, that there is an isometry between these two manifolds that depend only on the manifold in such a way that the zero order coefficient and one of the two internal sources are connected through this relation. So this is the first result that we obtained on a Riemannian manifold. Now let me move to our second result on the Riemannian manifold, which again will be stated for alpha not equal to 1 and on any interval in time of the form capital T0 minus delta capital T0, well, delta can be as small as we want. So here again, gamma in and gamma out are arbitrarily chosen. They coincide, but they are arbitrarily chosen. And we consider again the assumption of theorem 4, but this time the manifold will be fixed. We change only the metric. And in addition to that, we add some additional knowledge of the parameter on the part where we make our measurements. After that, what we show is that if the normal derivative of the solution and the normal derivative of this elliptic equation apply to the solution are known on any interval in time of the form capital T0 minus delta capital T0, where delta can be as small as we want, and with respect to the space variable on the part gamma out, then we get exactly the same result as in theorem 1. That is the recovery of the Riemannian manifold up to isometry and the relation that links the internal data and the coefficient. So this is the last result that I wanted to present. Now let me make some comments about this result. So the first thing that I would like to say is that this result are based on two works. The first work, which is a joint work with Ziren Li, Iken Liu, and Masairo Yamamoto, which will appear to mathematician Allen, and where we have treated the recovery of coefficient and Riemannian manifold without considering internal source, and with measurement on interval in time of the form 0 capital T0. And the second work, which is a preprint that you can find on arXiv in its incomplete form. It's some kind of work in progress. I will say at the end of this talk what is the progress that I would like to make on this work, on which I have considered the simultaneous recovery of internal source and coefficient. And I've been able also to restrict, in the fractional diffusion case, measurement to any interval in time of the form capital T0 minus delta capital T0. What we can say about the construction of our Dirichlet input is that it is inspired by the one introduced by Avden and Sedman, but also by Chen Yamamoto. However, we consider some Dirichlet input with several parameters for which we let some kind of freedom. We also adapt our construction to results stated with partial data, that is excitation and measurement on part of the boundary. And we can adapt this approach in some unified way, in such a way that you can apply our result to the parabolic case alpha equal to 1, but also to the time fractional diffusion case. And finally, you are able to adapt this type of approach in such a way that you can get simultaneous recovery of one of the two internal sources and the coefficient appearing in the equations. One of the important technical difficulty that appears in the proof of this type of result is based on some analyticity in time of solution of this type of equations that I will talk a little later on. And the idea is that these results are mainly difficult in the case alpha not equal to 1, and when you consider the solution of this type of problem with non-homogeneous Dirichlet boundary condition. The other thing that I would like to say about this result is that the main idea is to connect this type of data, that is single boundary measurement for this type of equations, to infinitely many boundary measurement for other type of inverse problems. So for instance, in theorem 1 and 2, we get information, data that can be used from our single boundary measurement. We can recover data that can be used into inverse spectral result. And here, the inverse spectral result that we use are the one given by Caputo and Kian in their work of 2004. In theorem 4 and 5, we managed to recover from our single boundary measurement for this type of diffusion equations the hyperbolic Dirichlet to Neumann map associated to a hyperbolic inverse problem, which is related to our problem. And then after that, we can apply the work of Katchalov, Krylev, Lassas that you can find in their book based on the so-called boundary control method in order to recover the Riemannian manifold and the different coefficient that appears in our equation. Finally, in theorem 3, the one where we deal with the convection term, we managed to get from our single boundary measurements the DN map for some families of elliptic equations, and then using the work of Salo-Pochola about the recovery of convection term for elliptic equation, as well as the work of Krupschik and Ullmann based on recovery of electromagnetic potential, we managed to recover the different coefficients appearing in our theorem. So let me say also a few comments about our results with the restriction of the measurement on any time interval of the form capital T0 minus delta capital T0, where delta can be as small as we want. So here we use actually the memory effect of these time fractional diffusion equations in a result which has been proved by Jano and Kinash and which can be stated as follows. It means this result says that if for any values of delta lying in the interval 0 capital T0, you know a function h on the interval capital T0 minus delta capital T0, and you know also its time fractional derivative on the same interval, then you have the full knowledge of your function on the full interval 0 capital T0. So of course, this result is not valid for alpha equal to 1. And this is the main reason why we restrict the result of theorem 2 and 4 to the case alpha not equal to 1. One interesting application of this result can be seen through the application of this result in the context of data on disjunct set. So the idea here will be to consider data on disjunct set with respect to the time variable. To see this, let us pick the parameter pk appearing in our Dirichlet input. I will show you what is the pk appearing here in our Dirichlet input to be equal to 0, which is of course allowed here in our construction. After that, let us pick capital T0, the time on which we make our measurement, to be strictly bigger than τ2. And let us assume that delta is strictly less than capital T0 minus τ2. What you can see is that the support of our Dirichlet input will be contained with respect to the time variable on the time interval 0, τ2. And we make here our measurement on the time interval capital T0 minus delta capital T0. So this means that the support of our Dirichlet input will not meet the part of the lateral boundary where we made our measurement. And we have here actually a result with data on these sets. Of course, as I said before, this result will not work for alpha equal to 1. In order to get results that works also for alpha equal to 1, we need to use result that will allow us to consider a result with data on disjunct set, but this time with respect to the space variable. And for this class of result, we can use the work of Lassas-Oksanen, who have proved the recovery of Riemannian manifold for hyperbolic equations from data on disjunct set, and also our work with Krylev, Lassas, and Oksanen, where we have been able to extend this type of approach to the recovery of coefficients. So here, the application in our context of this class of results requires some geometrical construction, geometrical restriction, imposed on the part where we apply our excitation and our measurement. So the first thing that we need to impose is the geometrical control condition of Pardo-Slobo and Roche on the part gamma in prime. And for the recovery of coefficients, we need to impose some strict convexity to the part gamma out for being able to apply our result with Kurylev, Lassas, and Oxel. Moreover, by using this type of approach, we can only get some local recovery of coefficients. So if we make now the comparison between this type of result and the result that we have obtained from with data on decision set with respect to the time variable, in the first class of results, that is the result with data on decision set with the respect to the time variable, we do not make any restriction on the gamma in prime. Gamma in prime can be chosen arbitrary, since the data are on decision set not with respect to the space variable, but with respect to the time variable. And moreover, we can get the full recovery of coefficient when this type of approach are only restricted to some local recovery of coefficients. However, as I said, our approach, which is based on the so-called memory effect that I have introduced you before, will not work for alpha equal to 1. So this is a bad point, actually, of this approach. So let me now conclude by recalling the main novelty of this work. So the first main novelty comes from the fact that we get the first result, what is, as far as we know, the first result of full recovery of parameter appearing in time fractional diffusion equations from a single boundary measurement. Even for alpha equal to 1, we obtain what it seems to be the first result of simultaneous determination of internal source and coefficient appearing in diffusion equations. In the case alpha not equal to 1, we can restrict our measurement to any interval in time as close as we want the final time of measurement capital T0. And we can apply this type of result to results stated with data on decision set that does not require geometrical restriction and allows to get full recovery of coefficients. So I would like to conclude this talk by giving an idea of the proof of theorem 1. So this is the easiest to present, actually. So let me recall the context for theorem 1. We deal with two types of equations and two classes of parameters of index j, j being equal to 1 and 2. And we start with this identity. And from this identity, we would like to show that the set of coefficient and the internal source coincide. So the first thing that we will do is to consider a family of initial boundary value problem that we introduce here. A family of initial boundary value problem 10 that depend on the index j, which will be the index of the equations. Here we have actually the same equations as we have for our initial problem, but the internal sources are fixed at 0. And we have a different Dirichlet input that make appears this index k that we can see in this type of solution. So in order to explain this Dirichlet inputs come from, let me go back to the construction of our Dirichlet inputs. Yes. So we pick as Dirichlet input each expression in this infinite sum. This is the type of Dirichlet input that we impose on this new initial boundary value problem. So each of these expressions allows us to define the following initial boundary value problem, which in contrast to the first initial boundary value problem will be defined on an interval in time of the form 0 plus infinity. The other initial boundary value problem will be considered with the same equations, but with Dirichlet boundary condition fixed at 0 and all the internal source that appears this time. And now the first thing that we can say is some analyticity property of the solution of this initial boundary value problem. For the solution of the first class of initial boundary value problem, that is the initial boundary value problem 10, what we can say is that this solution will be analytic restricted to the time interval t to the index 2k minus 1 plus infinity as function taking value in hs of omega with s strictly bigger than 3/2. So here, this time analyticity comes from the fact that this Dirichlet input will be independent of the time variable after this time t to the index 2k minus 1. The second thing that we can say is that due to the fact that the support of the time-dependent part of our source time is contained into 0 to 1, we can pick a sufficiently small epsilon in such a way that the support of this expression will be contained into an interval of the form 0 to 1 minus 2 epsilon. And after that, what we can see is that the restriction of the solution of this second initial boundary value problem on the time interval t0 minus epsilon plus infinity will be an analytic function as a function taking value in hs of omega. So here, I recall that t0 will be equal to tau1. This is what we use here. So now combining this analyticity property with the fact that if you pick the infinite sum of the solution of this initial boundary value problem, that you take this sum with respect to the k index, and you take these values of this expression at x lying on the boundary of our open set, you can see that you get exactly the directly input capital phi. And this directly input capital phi will be exactly the values of the solution of the first initial boundary value problem that we have considered. Combining this with the initial identity that we have and the analyticity property that I have described above, we get this infinite number of identity. The identity that's saying that the normal derivative of the solution of the initial boundary value problem 10 with index k coincide for all k. And you have also this coincidence for k equal to 0 here. So we have these two classes of infinite identity. And the idea will be to use the first class of infinite identity in order to recover the coefficient, and then to go back to the second class of identity in order to recover one of the two internal sources. This is the main idea that we exploit here. So let me first show how we get the recovery of the coefficient from this first class of identity. The idea is to consider the following boundary value problem, depending on the parameter pi. A boundary value problem that we can get by applying the Laplace transform in time to the problem 10. So here we have these families of boundary value problem, and we can associate to this boundary value problem, family of boundary value problem, a partial Dirichlet to Neumann map, depending on this parameter pi. So this partial Dirichlet to Neumann map sends any Dirichlet input supported on the closure of gamma in prime into the normal derivative of the solution of this boundary value problem, weighted by the conductivity that we consider on the part of the boundary gamma out. So here, using the first class of identity, which is this time valid for all time, combined with the fact that if you apply the Laplace transform to each of these solutions and you take the value at the boundary, you obtain an expression depending only on the parameter pi times the cutoff function and the function eta k, where we recall that the span of the function eta k will be dense in H3/2 of the boundary of our open set. And using this type of properties, what we get actually from our data is the full knowledge of these families of Dn map for all parameter pi strictly positive. And we will use this type of data in order to recover our coefficient. And the idea will be to connect this type of data to boundary spectral data. For this purpose, we consider these two elliptic operators of index j, which correspond to the elliptic operator associated to our boundary value problem. And we consider this operator as an operator acting on the space L2 of omega, with measure having the density rho j, and some Dirichlet inputs, some Dirichlet boundary condition. After that, the first thing that we can say is that this elliptic operator are self-adjoint. And thanks to the compact Rutherford argument, we can say that the spectrum of this operator consists of a non-decreasing sequence of eigenvalues that we consider here repeated with respect to their multiplicity. And the idea now is to use the fact that the Dn map of these families of elliptic operator coincide with some work based on the representation of the solution of the problem 13 given by Caputo, Kian, and result that we have also considered with Oksanen, Soccorsi, and Yamamoto, in order to prove that there exists an orthonormal basis of eigen functions associated to our eigenvalues for each of these operators, in such a way that, first of all, the eigenvalues of each of these operators repeated with respect to their multiplicity coincide, and secondly, the normal derivative of this eigenfunction weighted by the conductivity coincide on the boundary of our open set. And now the idea is to use an inverse spectral result, which is due to Caputo and Kian, in order to prove that from this identity, we can get the full recovery of our coefficient. So now that we have been able to prove the full recovery of the coefficient, we can move to the recovery of the internal source. And we will use here the data that we have for this function V0j. And what we know is that we have these two same equations with some different internal source and the normal derivative of these two solutions that coincide. And from this type of identity, we are able to prove the recovery of the internal source. So this completes the proof of theorem 1. So now I would like to complete this talk by two prospects. So the first prospect actually is not really a prospect. It's some work in progress, because as I say, the work that I have put it on archive for what I have presented in this talk is not finished. The final version will include the resolution actually of 3 among the most important inverse problems stated for partial differential equation that we would like to solve in one shot. That is inverse source, inverse obstacle, inverse coefficient. So I would like to add to what I've considered so far the recovery of an obstacle. So the idea being that from a single boundary measurement comparable to the one that I've introduced, with the same class of direct inputs, we want to recover obstacle, source, and coefficients. The other prospect corresponds to some extension of this type of approach, which are so far restricted to coefficients that depend only on the space variable, to coefficients that may depend also on the time variable. So the first class of problem that we want to consider in that context will be stated in the case alpha equal to 1, and coefficient that will be analytic with respect to the time variable, in order to be able to expect at some point to adapt the approach of Abdonin and Seidman in this framework. So that's it. Thank you for your attention.
Thank you very much, Yavar, for the very nice talk. Thank you very much. Are there any questions or comments? Please unmute yourself. Are there any questions or comments?
Okay, I have a question.
Please.
However, so you mentioned at the beginning that there are several definitions of fractional derivative with respect to time, and you choose one of them because somehow, I don't know, mathematically it looks better maybe.
Physically it is better.
Okay, actually that was my question. Why is that the physical choice? I mean, you're coming from center of theoretical physics, you should know.
As I said, I'm pure mathematician. But the idea is that mainly you have the behavior for Cauchy problem. Here, the initial condition will be usual initial condition, the one that you consider in the usual derivative. While with the Riemann-Liouville one, you will deal with some non-local things. And moreover, you have also the behavior against constant function. While the Caputo one vanish constant function, the Riemann-Liouville one will not vanish them. So physically, I believe that the definition of derivative should at least vanish constant function. This is maybe one of the main reasons why they go for the Caputo one instead of the Riemann-Liouville one.
Okay, thank you.
Thank you very much. I also see a raised hand. Please unmute yourself and ask questions.
Yes, hello. My question is, you speak of recovery, or is it just injectivity, or is it actually an idea of an algorithm to identify the coefficients?
So it's injectivity. Here I mean injectivity, but identifying the coefficient, it depends on what you mean about identifying the coefficient, but no, we have not considered that direction, but it will be an interesting direction. Here I mean only injectivity. I have only speak about uniqueness result.
Thank you very much. Are there any other questions or comments? Okay, probably not. Thank you very much, Yavar, for the very nice talk.
Thank you, Katya.
Thank you very much, everyone, for coming. Thank you very much. Thank you.
Thank you. Thank you.